Welcome students. In this part we are going to see the topic percentage composition of a compound. So we are the first chapter, some basic concepts of chemistry. So in this chapter we are going to see the topic today, percentage composition of a compound. So percentage composition is nothing but percentage of various atoms present in a compound by mass. So percentage composition is the percentage of various atoms present in a compound by mass. So how to get the percentage of an atom present in a compound? So we can use the formula of percentage calculation. You might be familiar with this formula in your lower classes, how to find the percentage of something. So mass percentage of an atom, since it is the percentage of mass, you can call it as mass percentage of an atom in a compound. So I am going to find out percentage of an atom in a compound is equal to mass of the atom in the compound divided by total mass of the compound into 100. So this is the formula to calculate mass percentage of an atom in the compound. How to do it? You just take mass of the atom in the compound, you divide it with total mass of the compound into 100. So this is how you can calculate the percentage composition of a compound, or you can calculate the percentage of an atom in the compound. So if you are doing this for the entire atoms in the compound, you can find out the percentage composition. Clear? Let's look into an example. So what is the percentage composition of NaOH? So what are the different atoms in this molecule, in this compound? We have sodium atom, we have oxygen atom, and we have hydrogen atom. So in order to find out the percentage composition, I have to find out the percentage mass of sodium, then I have to find out the percentage mass of oxygen, and then I have to find out the percentage mass of hydrogen. So I know the atomic mass unit of sodium, that is 23, atomic mass unit of oxygen, that is 16, and that of hydrogen is 1U. And also I know the atomic mass unit of the entire molecule, or you can say molecular mass. If you add them up all, add the atomic mass of all the atoms, 23 plus 16 plus 1, you will get the mass of sodium hydroxide, molecular mass. Either you can go for molecular mass or atomic mass, or you can take molar mass. They are both the same. Only difference is that this is the mass of an atom, whereas if you are taking this in grams or molar mass, that is about 1 mole. So literally they are not same, but you can say that magnitude wise they both are the same. So you have got the mass of each atom and have the mass of the entire compound. So how to apply this into the formula? We have the formula like this: mass percentage of sodium of one atom, sodium, is equal to its mass in that compound, that is 23, divided by mass of the compound into 100. So what's the answer? 57.5. 57.5%. Similarly, you can calculate the mass of oxygen. What to do? Again, applying the formula: mass percentage of oxygen, that is mass of that atom in the compound. You have only one oxygen atom, so it is 16U, divided by mass of NaOH, that is 40U, into 100. So you will get 40%. So similarly for hydrogen, you have instead of O, it is hydrogen. So I will make the correction using pen. So this is not oxygen, this is hydrogen. Okay, so we have hydrogen, its atomic mass unit is 1 divided by the mass of the compound, that is 40 into 100, which is equal to 2.5. Or you can get it by, since there are only 3 types of atoms, you can take 100 minus U subtract these factors, then you will get the mass of hydrogen, or you subtract these two and you will get the mass of sodium. So accordingly, if it is an entrance exam, you can save time in this way, whereas if it is a board exam, you can do and try to find out whether the sum of the three is 100 or not. So you can verify that in that way. Okay, so percentage composition of NaOH is finding the mass percentage of each atom. So I have found out the mass percentage of sodium, I have found out the mass percentages of oxygen, and I have found out the mass percentage of hydrogen. So if I am taking any mass of sodium hydroxide, say if I am taking say, let's write, so 100 gram of sodium hydroxide. Imagine that I am taking 100 gram of sodium hydroxide. If I am taking 100 gram of sodium hydroxide, in that 57.5 percentage will be sodium, 40 percentage will be oxygen, and 2.5 percentage will be hydrogen. Means in 100 it is easy to calculate. If we have percentage, 57.5 gram will be sodium, 40 gram will be oxygen, and 2.5 gram will be hydrogen. So this is the use of this percentage composition. If you know that percentage composition, you can calculate the mass of that particular atom in any given mass. So here it is 100 gram. If it is 1 kilogram, if it is 1.5 kilogram, you can calculate how much sodium is present inside it. Clear? Okay. Next question. What is the percentage composition of oxygen in 250 gram of CH3COH? So if it is specifically mentioned about a particular atom, then you don't have to calculate the composition of all other atoms. You can specifically calculate the composition. So what they have asked here is about the percentage composition of oxygen. So you can calculate that percentage composition of oxygen from they have asked to calculate it from 250 grams. So first, what should I do? I should find out mass percentage of oxygen in 1 CH3COH, in 1 mole or 1 molecule of CH3COH. Okay, so we will start like this. What is the molar mass of CH3COH? Either you can go for molar mass or you can go for molecular mass. Both are magnitudely the same. So molar mass of CH3COH, we have seen this many times for acetic acid. So this compound is acetic acid, CH3COH. How to get the molar mass? You just find the molecular mass. How to find molecular mass? You just add the atomic masses. So we have 2 carbon. Each carbon is having 12 U. So 12 into 2, which is equal to 24. And we have 2 oxygen, that is 16 into 2, that is each oxygen is having 16 U. So we have 2 such atoms. So 16 into 2 is equal to 32. And we have 4 hydrogen, and each hydrogen, mass of each hydrogen is 1. So 4 into 1 is equal to 4. So you add them up, you will get the value 60 gram per mole. 24 plus 4, 28, plus 32 is equal to 60 gram per mole. So you have the total mass or mass of CH3COH. Now what they have asked is to find out the percentage composition of oxygen. So I should first find out the mass of oxygen in this 60 gram. So for that, mass of O is equal to, I have 2 atoms, right? So 16 into 2, which is equal to 32 gram per mole. So out of 60, 32 is oxygen. So how to find out the percentage? Mass percentage of O is equal to 32, that is mass of oxygen, divided by the total mass of the compound, that is 60 into 100. So the answer will be 53.33%. Clear? Now what is the percentage composition of oxygen in 250? So if in 60 gram, if it is 53.33 percentage, in 250 gram also it will be 53.33 percentage. So in 250 gram of CH3COH, 53 percentage will be O. Clear? So in 60 percentage, if it is 60 gram, if it is 53.33 percentage, then in 250 gram also it will be 53.33 percentage. Percentage will never change, whereas mass will change, but mass percentage will be always the same. Clear? So what I need to find out is 53 percentage of 250 gram. So percentage calculation is like this: mass of O divided by total mass is 250 into 100, which is 53.33. What I have to find out is mass of O. So I will try to rearrange the equation. Mass of O is equal to 53.33 into 250 by 100, which is equal to 133.33 gram. Just try to verify more than 50 percentage. More than 50 percentage of 250 is 125 above. So it is approximately that value, which means that our calculations are correct. So 133.33 gram of gram will be oxygen in 250 gram of this acetic acid. So next we are going to see the topic empirical formula. We are in the chapter some basic concepts of chemistry. In this chapter we are going to see the topic empirical formula. In the lower classes you might have learned about empirical formula and molecular formula. Let's make a quick look into the definition for empirical formula and molecular formula. So molecular formula is nothing but, in a molecular formula it shows the exact number of atoms present in a molecule. So molecular formula is to demonstrate the atoms that is present in a molecule, exact number of atoms. Clear? For example, molecular formula of glucose is C6H12O6. But unlike molecular formula, in empirical formula it shows their simple whole number ratio. Simple whole number ratio of atoms present in a molecule. So that's the difference between empirical formula and molecular formula. Molecular formula actually shows all the atoms in their ratio present in a molecule, whereas empirical formula shows the ratio, just the whole number ratio between them. So I have the molecular formula of glucose here, that is C6H12O6. What will be their ratio? If I am taking out the common factor from it, it will be 1:2:1. That simple whole number ratio will be the empirical formula. So how can I write the empirical formula of this compound? Can be written like this: C1H2O1. Since 1 is understood, we will not write that specifically. Clear? So empirical formula, I think it's clear from this example. Difference between molecular formula and empirical formula. If it's molecular formula, it gives a clear picture of how much atoms and what are the atoms and how much atoms are present. Whereas for empirical formula, they will show how much atoms, what are the atoms, but it will not show how much atoms are there. So you can say that this is quality. This shows the quality, that is how much or what are the atoms present. Whereas molecular formula is quantity, how many or how much atoms are present in a molecule. So this is quality and this is quantity. So maybe I will write it down because it is not mentioned here. So this is quantity, whereas this is quality. So empirical formula is quality, what atoms are present, their simple whole number ratio, whereas molecular formula is their quantity. Clear? Whereas in certain compounds or in many compounds, both molecular formula and empirical formula are the same. Here are the few examples. For example, water, H2O, it cannot be further simplified as far as ratio is concerned. So both EF and MF will be the same. Whereas in the case of carbon dioxide also, we have the same molecular formula, or the empirical formula is same as the molecular formula. And we have here the table sugar or sucrose C12H22O11. Though their size number of molecules is quite huge, you cannot simplify them. Clear? So there are many molecules whose molecular formula and empirical formula are the same, whereas there are molecules whose empirical formula and molecular formula are different. So next is we are going to determine the empirical formula and molecular formula of compounds, how to determine them. So what are the essentials that is required to determine the empirical formula and molecular formula? Empirical formula can be calculated from the percentage composition of a compound. So we have seen how to calculate the percentage composition of a compound. You can calculate the empirical formula from the percentage composition of the compound. For molecular formula, apart from the percentage composition, you also need the molar mass of the compound. So in order to calculate the molecular formula, you need percentage composition and molar mass of the compound. So instead of percentage composition, you can also use empirical formula. So instead of percentage composition, you can use empirical formula and molar mass. So for molecular formula, to get molecular formula, one thing is essential, that is molar mass. Either you can use percentage composition or you can use the empirical formula along with molar mass to determine the molecular formula. So next we are going to see how to do this calculation. Here you have a problem to find out the empirical formula and molecular formula of a compound. So the problem is they have supplied with the composition, percentage composition. Hydrogen percentage is here, carbon percentage is here, and chlorine percentage here. They have also provided the molar mass, that is 98.96 gram per mole. They have asked to calculate the empirical formula and molecular formula. So to do this, we are going to construct a table. So if you are constructing a table like this, it will simplify your calculation. So first you have to write down the atoms present. So in the question it is given hydrogen, carbon and chlorine, and their percentage is also supplied, percentage composition. Now using the formula for percentage calculation, you can find out the mass in this molar mass, that is 98.96. So if you are calculating for hydrogen, you substitute the values here, 4.07 into 98.96 divided by 100, that is 4 approximately, 24 and 70.9. You can calculate by substituting their percentage, each percentage here. Then you must know their molar mass. In one of our earlier parts we have by hearted the molar mass of hydrogen, carbon, or their atomic mass. So molar mass is nothing but their atomic mass by magnitude. So hydrogen is 1, carbon is 12, and for chlorine it is 35.5. So how to get the number of moles then? We have learned this formula also. N is equal to mass divided by molar mass. So what is the mass? 4 divided by 1, which we have 4 moles of hydrogen in 98.96 grams. Next, for carbon, it is mass is given 24 divided by 12, that is equal to 2. And then for chlorine, it is 70.9 divided by 35.5, which is also equal to 2. So in 98.96 we have 4 moles of hydrogen, 2 moles of carbon and 2 moles of chlorine. So what is the molecular formula then? That is C2H4Cl2. C2H4Cl2. So you can further simplify this into simple whole number ratio, which is the empirical formula, that is CH2Cl. So this is the real number of atoms in a molecule and this is their ratio. So this is a quality and this is the quantity. Clear? So next one. Determine the empirical formula of an oxide of iron which has 69.9% iron and 30.1% dioxygen by mass. So they have given the composition, percentage composition, and they have also supplied the molar mass of Fe. So they haven't given the molar mass of molecule, which means that it is not possible to calculate the molecular formula of this oxide, of this compound, oxide of iron. Clear? So we have to assume a number. So let's see how to use the table for this. So we have two atoms, Fe and oxygen, and also we have their percentage, 69.9 of Fe and 30.1. So we are considering the mass as 100 grams. Since the molar mass is not provided, molar mass of the oxide is not given. Molar mass of iron is given, but not that of oxide. It is 100 grams. I am assuming it as 100 grams. So if I am assuming it as 100 grams, you can easily get this mass of iron present in it. That is 69.9, 30.1. I know the molar mass. Molar mass of iron is given and molar mass of oxygen is 16. So since I know the mass, what I can do is I can find the number of moles of iron present in this mass and number of moles of O present in this mass using this formula. N is equal to mass divided by molar mass. So if I'm doing that, I will get 1.25. That is mass 69.9 divided by 55.8. That is 1.25. And in this case, mass is 30.1, which is divided by 16. That is equal to 1.88. So as you can see that the number of moles are not whole number. For writing the formula, you need whole number values. So what I want to do is I want to make this into a whole number. For that, I will choose the lowest number. Which is the lowest number? 125 is the lowest number. I divide this lowest number. Using this lowest number, I divide both the values. So when I'm dividing with 1.25, it will become 1. When I'm dividing with 1.88, again there is a fraction. So that means that again I should do something else to make it into a whole number. So it's very easy. 1.5 will turn into a whole number if I'm multiplying it with 2. So if I multiply this, I should also multiply this number. So if I'm multiplying both, I will get here 1 into 2 is equal to 2, 1.5 into 2 is equal to 3. Now it is a whole number. So what will be the empirical formula? Empirical formula is Fe2O3. So this is how to find out empirical formula. But I cannot find out the molecular formula unless if the molar mass is supplied. Otherwise I can deduce, because there is a molecule like Fe2O3, and since the empirical formula I got is this, the molecular formula can be this one. But this is only a guess. In real life, if you want to get the molecular formula, its molar mass must be supplied. Clear?